Hello class, in this lesson we're going to be learning about the law of sines and cosines. Let's start off with a triangle like this. Suppose I call this x. I want to figure out what x is. I'm going to tell you that this length of this side is 12 and that this is a 32-degree angle. Can I figure out x? The answer in this case is kind of a trick question, is no, because I've only told you this side length and this angle here. This is not a right triangle. I did not tell you that it was. Since I only have two sides of information, from our geometry days, we knew about kind of different congruence theorems, SSS, SAS, ASA, HL, or AAS. These were different ways, and in each case here, I depended on knowing three pieces of information in terms of either side congruencies or angle congruencies. If I only had two pieces of information, I would not be able to claim triangle congruency between two different triangles with these same measures. And, even in this case here with HL, we are kind of knowing that we know a side, another side, and an angle to be 90 degrees. So two pieces of information does not allow us to figure out this third side here, or this other side. And in all that we've been doing with trigonometry, we always depended upon this being a right angle, but suppose it were 92 degrees. Today's lesson, we're going to talk about how we deal with cases where we have three pieces of information, and from the congruency theorems, this is angle, angle, side. There is only one triangle that fits this 92, 32, 12 specification for a triangle. So we're going to figure out the way to discover what x is, what this other angle is here, and what this other length is here. We're going to learn that the law of sines and the law of cosines work to solve any type of triangle. And we're going to talk about an ambiguous case where the law of sines can help us find two solutions. And we're also going to talk about Heron's formula, where we calculate the area of a triangle. Law of sines says this, that there is a ratio between the angle A and its opposite side. The ratio between those, the sine of A and the opposite side, this is equivalent to the sine of B divided by its opposite side. And that's the key thing. We're talking about opposite angle side pairs. So we're always looking at these kind of combinations of ratios between the sine of the angle and its opposite side. So in the case of, say, a triangle where we're given two angles and one side, that would be, say, a AAS case or a ASA case, we could find everything else. We could find the third angle just with geometry, 180 degrees minus the measure of the two angles. And then we use the law of sines to find the other missing side lengths. So for example, we have a triangle where we know two angles, and we know that the opposite side length to angle A has a measure of 8. So it's not totally necessary, but let's sketch it out anyways. So we have angle A and opposite to it, 8. Then we have 25 here for angle B, and we want to find everything else about this triangle. This side length, as well as this angle. Starting with this angle, that's the easy part. Just 180 degrees minus 125. So that's 55 degrees for this angle. Now we're going to use the law of sines to figure out what B is and what C is on this triangle. So we're already, we could plug in the ratio sine A over A. And then we just plug in sine B over B, sine C over C. So I'm going to first solve for B. I'm going to just ignore this equation, or this part of the equation here. I'm just going to look at these two here and solve for B. And when I do that, I get 8 times the ratio of sine 25 over sine 100. I plug all of this into my calculator, I get 3.43. Now I do the same thing to solve for C. I'm just going to ignore this middle piece, and I'm going to use the given information. This is equal to this over here, and I'm going to solve for C. In this case, I get 6.65. Now, this is what we call the unambiguous case, so that leads us to actually the more interesting case, which is the ambiguous case. It's ambiguous because in a case where we're given a side, and an angle, we know from geometry there is no SSA congruence theorem. Because actually we can get multiple triangles if we're given a specification with S, S, and A. And let's kind of talk through that and see where that ambiguous case actually is. We're going to look at several cases. First case is when the angle A is less than 90 degrees. So I have my side opposite it, and I have my angle B, or side B. But in this case, so I'm given A, the opposite side, as well as length B. In this case, I know that H here, the height, is equal to B times sine A. And this is just using right triangle trigonometry. Now, in this case, you can see that A is too short. It actually can't even touch this bottom line here. So in this case, we actually don't have a solution. There is no triangle in the case here where A is less than B sine A. We cannot make a triangle out of this. In the case where A is exactly equal to H, when A is equal to B sine A, there is a triangle. There's a right triangle. That's our single solution. Now, in the case here where A is greater than H, but it's less than B, we have a case where we can kind of imagine that this line of length A kind of swings back and forth right on this, and it has two intersection points, and we can actually imagine two different triangles, triangle 1 in yellow and say triangle 2 in green. Both of them have an angle measure A, both of them have a side measure B, and both of them have a side measured A. And this is why there is no SSA congruence theorem, because we have this ambiguous case where there are two triangles made up with the same SSA. So, two solutions. A third case is when this side length opposite the angle is bigger than B. In this case, there's only one solution. We have another case, now a whole other set of cases when the angle is greater than 90 degrees. So actually ignore this. When angle A is greater than 90, again we have a case similar to this where A is less than B, and it's just too short. It will never be able to touch this line down on bottom. No solution. The last final case is when A is greater than B. We can connect up over here, and we get one solution for this triangle where we have an angle A here, side opposite, and we have B. Now you might be thinking to yourself, wow, I have to memorize each of these four different solutions. I have to calculate H. I have to do all this and that. And that is legitimately one method of doing things, but the nice thing about mathematics is that the numbers actually just work out. Let me go through a few examples to show you what I mean. In this case here, let me sketch out the picture of it. In this case, we actually do not expect any solution because this length 3 here, opposite the 30-degree angle, it's just too small, and it won't. The height here is 5, 1/2 of 10, or 10 times sine 30, which is 5. It's too short. It's not going to reach. We have no solutions. Let's see what happens when we apply the sine, the law of sines to it, though. When we apply the law of sines, we get sine 30 over 3 is equal to sine b over 10, and this then, reduces to sine b is equal to 5/3 But there is nothing. There is no sign that will give us an answer that's greater than 1. So there's no solution for this, which is nice. The mathematics actually worked out, and so it's nice. It gave us the same consistent solution, you know. Now let's look at the next case here. This case, we expect two different solutions. A is greater than 5, the height, but it's less than 10, the length of B over here. Two solutions we expect. Let's see what happens. So I run through my law of sines, and I get the inverse sine of 5, 6, which is 56.4. Now I know that I can actually find an alternative solution by subtracting from 180, because, remember, just to recall, if I had one angle here as a solution, I know I have another solution on this other side here where the sines are the same. The height of this triangle and the height of this triangle, they're exactly the same. They have the same sine value. So in this case, yeah, you can imagine this angle right in here where the finger is pointing is 56 degrees, and in this case the angle right in here where the finger is 123 degrees, both legitimate answers. And that's the nice thing about this. Again, we expected two solutions, we got two solutions. Okay, so let's look at one last case when there's only one solution now. How do we see this case happen? So again, I'm going to set up my law of sines equation, and I get 24.6 for this angle right in there. But just like I did over here, I could generate another solution. Subtracting it from 180 degrees, I get 155 degrees. But I only expect one answer, so what's up with that? Here we can see this. If I took 155 as angle B, but then I added it to 30, now all of a sudden it's greater than 180. There is no triangle it's too big. I cannot make another triangle with 30 degrees and 155 degrees for another angle. So again, the nice thing about this case is we didn't even have to figure it out or think about it or remember all the, those 6 cases on the previous page. The math worked itself out when we applied the law of sines. We got one answer. We do generate the second angle solution, but we then refer back to the picture and say, wait a second, it cannot be true. This is too big. Okay, let's look at the law of cosines now, because, we have some triangles here. Suppose I told you this is 5, 7, and, 8. In this case, I have no angle information. So I can't use the law of sines to calculate any of these angles here, because I need to have at least one angle information for the law of sines to work. So this is where the law of cosines comes into play. Law of cosines can be used for triangles where we know SAS, the angle is the included angle, or SSS, where we're not given any angles at all. In this case, here is the law of cosines, and I wrote out two kind of equations, one where it's solving for a side, the other where it's solving for an angle, but they're equivalent. Note here that C is not always the longest side. You might be used to the C squared is equal to A squared plus B squared, being your Pythagorean formula, and C squared is always your hypotenuse. But in the law of cosines, that's not the case. The C can be any side length as long as this little c that we're using here is opposite the angle that we're using in the cosine. So the key thing is that when we're applying this equation, the c's are opposite side angle pairs. The C is the included angle between the two sides that we know and are using. So actually ignore the A, B, and C. I'm just going to take this triangle and draw it out. I want to figure out this angle here. And I'll just label this angle like that. And I'm going to label the side opposite to it 14 and 8 and 19 here. And at this point, I'm just going to kind of cross out all this information. I don't want you to see that, actually. Now, I want to find this angle here. We'll call that C, given this triangle. So in this case, I'm going to consider the fact that these are the opposite pieces, and so these are going to be kind of like my C and C, my big C, my angle C, my little c, the side length. And now I'm going to plug this into this equation here, where 8 and 19 are my A and B respectively, and the order doesn't matter whether it's, 8 is A or 19 is A. So I plug that into my equation, and I get the inverse cosine of this, which is 41.12 degrees. Okay, let's keep going. Suppose now I have this equation over here, and now I don't have any information here for x, but I know that I can use the law of cosines across, using these two pieces of information. So again, I'm going to set up my going to start off with my quote-unquote Pythagorean equation formula, but now I'm going to throw in this minus 2ab cosine c term, and in this case, if we solve it, we get 7.4. Okay, so that's law of cosines. Last case here, I'm going to show how to use Heron's formula for calculating area. It's pretty straightforward. Here's the equation right over here. To figure out the area, we figure out the average of all the side lengths. The average is 13. And then we're going to plug that into the formula that we're just given right here. We plug all the side lengths in, simplify it, we get 18.74. Okay, that's the lesson for today. Have a good day, class.